Hello, my dear students, and a very warm welcome back. Have you ever wondered why you feel that lovely cool breeze at the beach in the afternoon? Or how a simple wind can turn into a huge, powerful cyclone? Well, this chapter has all the answers. I know exams are just around the corner, and this topic, it can feel a bit confusing, but please don't worry. In the next few minutes, we're going to make it absolutely crystal clear. So grab your notebook, hit that subscribe button for me, and let's get started.
I can almost feel the exam tension in the air. But bachcho, fikr not. Your favorite tutor is here, and trust me, together, we are going to make this chapter so simple, you will feel like a weather expert by the end of it. So let's start with a positive mind, okay? Ready to begin?
Okay, let's dive right in. The single most important concept, the foundation for this whole chapter, is air pressure. Seriously, everything, from a gentle little breeze to a terrifying cyclone, it all starts with this one simple idea. So let's break it down. Now, don't let this textbook definition scare you away. It sounds way more complicated than it is. Just imagine a huge, invisible pillar of air. It's stretching from the top of your head all the way up into space. All of that air, it has weight, and it's pressing down on you. That weight is what we call atmospheric pressure. See? Simple as that. This little drawing shows it perfectly. See that column of air? It has weight, and it's creating pressure on the ground. Think of it like a stack of books, you know? The book at the very bottom is the most squashed one. It's the same with air. The air at the surface is denser because of all the air pressing down from above. And that means the pressure is highest right here where we are. Now, this is a number you absolutely must remember, Bacho. Put a star next to it in your notes, 1013.2 millibars. This is the average pressure at sea level. It's our starting point for everything else. I've seen this pop up as a one-mark question so many times, so please make sure you know it. So you might be thinking, if this pressure is everywhere, why isn't the air just still? Why do we even have wind? Well, the answer is pretty simple. The pressure isn't the same everywhere on Earth, and it's these differences in pressure that get the air moving. Let's explore the forces that are behind it all. This slide, my dear students, this is the golden rule of this entire chapter. If you remember only one thing, please remember this. Wind always moves from an area of high pressure to an area of low pressure. Always. It's just like water flowing downhill. It's a basic law of physics. But here's the thing. The wind doesn't just move in a simple straight line. Oh no. It's guided by three main forces. First, you have the pressure gradient force. That's the main push from the high to the low pressure. Second is the frictional force. Think of this as the drag from the Earth's surface, mountains and trees slowing the wind down. And finally, the most interesting one, the Coriolis force, which gives the wind its spin. And this brings us to the Coriolis force. It's a little tricky, but it's super important. Because our Earth is constantly spinning on its axis, it makes moving things, like wind, look like they are curving instead of going straight. It's a bit of a mind-bending concept, I know, but it is absolutely essential for understanding how big weather systems, like cyclones, actually form. And here's the main takeaway. In the Northern Hemisphere, where we are in India, the Coriolis force pushes the wind to the right. In the Southern Hemisphere, it pushes it to the left. Just remember this for your exam. Right in the north, left in the south. Simple. Okay, time for a pop quiz. Exam question alert. This is a classic board exam question, so listen carefully. Based on what we just learned about the Coriolis force, can you tell me why we never see tropical cyclones forming right at the equator? Take a second to think about it. And here's the answer. It's because the Coriolis force is pretty much zero at the equator. It's strongest at the poles and gets weaker and weaker as you get closer to the equator. And to form a cyclone, you need that spinning motion. So no spin, no cyclone. That spin is the key ingredient for these huge storms. All right, now that we understand the forces, let's zoom out. Let's look at the big picture, the Earth's permanent wind patterns, what we call the global wind belts. This is where all those ideas we just talked about, pressure, forces, spin, all come together on a planetary scale. Now, I know what you're thinking. This map looks really complicated, but please don't worry. This is our hero slide for this section. You see those H's and L's? Those are the permanent belts of high and low pressure that circle the entire globe. And the arrows, they show the major winds flowing between them. We're going to break this down, cell by cell, nice and easy.
So this global circulation is basically driven by three giant conveyor belts of air in each hemisphere. We call them cells. First is the Hadley cell. That's in the tropics. It lifts hot, moist air up at the equator. Then you have the polar cell right at the poles, sinking cold, dense air. And kind of sandwiched in between them is the feral cell. Together, these three cells work to move heat from the warm equator to the cold poles, which helps to balance our planet's temperature.
Okay, enough with the big global picture. Let's bring it right down to something we've all experienced. I'm sure if you've ever been to Juhu Beach in Mumbai or Marina Beach in Chennai, you've felt that beautiful, cool breeze that starts in the afternoon. Well, that's a local wind, and it's created by the very same pressure differences we've been talking about this whole time. Here's how it works. It's really simple. During the day, the land heats up much, much faster than the sea. This hot air over the land rises, creating a low-pressure zone. Meanwhile, the sea stays nice and cool, creating a high-pressure zone. And what's our golden rule? Wind flows from high to low pressure. So we get a cool, refreshing breeze blowing from the sea onto the land. And that, my friends, is the sea breeze.
Then, at night, the whole process just flips. The land cools down much faster than the water, so it becomes a high-pressure area. The sea, which has held onto its warmth, is now a low-pressure area in comparison. So the wind changes direction and blows from the land out to the sea. We call this the land breeze. See? It's all just simple, beautiful logic.
And now for the grand finale, the most powerful and the most dramatic topic in this whole chapter: cyclones. This is where all the concepts we've learned, pressure differences, wind, the Coriolis force, they all come together to create nature's most destructive storms.
Pay very close attention to this slide, Butcho, because differentiate between tropical and extratropical cyclones is a very, very common exam question. Tropical cyclones, like the ones that form in the Bay of Bengal, are born over warm oceans. They're smaller in size, but they are incredibly destructive. Extratropical cyclones, on the other hand, form at higher latitudes, can develop over land, and they affect a much larger area. Make sure you note down these key differences. This amazing image shows us a cross-section of a mature tropical cyclone. You can see it's this giant spinning engine of clouds and wind. But notice that calm spot right in the middle? That's called the eye. And that powerful wall of clouds all around it is the eye wall. Let's look a little closer at these two parts.
So right in the center, you have the eye of the cyclone. It's a surprisingly calm and clear area, but don't let that fool you. Surrounding it is the eye wall, and this is the most dangerous part of the entire storm. This is where you'll find the most violent winds, sometimes over 250 kilometers per hour, and the heaviest torrential rain. Now, the most important thing to remember here is that a tropical cyclone is like a giant heat engine. Its fuel is the warm, moist air that it sucks up from the tropical oceans. So, as you can see in the diagram, as soon as it moves over land, its fuel supply is cut off. Without that warm water, it quickly loses all its strength and dies out. And there you have it. From simple air pressure to the immense power of cyclones, we've covered the entire chapter. You have done a fantastic job, Butcho. Review your notes, maybe watch this again if you need a quick refresher, and please, walk into that exam hall with full confidence. You've got this. All the very best.